Hello.
Okay, hello everyone.
Hello.
Hi there. Welcome to the Turkish Academy of Science World Conference on Energy, Science and Technology. This is General Session 6, and we are going to start the session on renewable energy. This is the second renewable energy system session. Okay. Technically, we have 6 presentations and 90 minutes, which means that 50 minutes will be dedicated for each respective presenter. So we can have around 12 minutes presentation and following 2-3 minutes for the QA sessions. So my name is Nader Javani. I'm faculty member from Yıldız Teknik University. And I would like to start the session with the first presentation from paper number 18. The subject of the first presentation is potential use of renewable energy for rural electrification in Pakistan by incorporating the blockchain technology. And I think Mrs. Rana will present the study. Rana, floor is yours, and you have 12 to 13 minutes for this presentation. Thank you.
Okay. Should I start now?
Yes, you can start, please.
Okay. Okay. Okay, I'm Aksarana.
Okay, we can see your presentation. Okay, now you can go ahead.
Okay. I'm Aksarana. Basically, I'm from Pakistan, but now I'm doing PhD from Budapest University of Technology and Economics. And here in Hungary, under the supervision of hello?
Yes, we can hear.
But it's fluctuating for me.
Everything is fine here. We can see.
Okay. But I couldn't see anything. There is a blank screen for me. A moment, please.
We have your cover page, the title of presentation, and looks like there's no problem from our side. So
for me, the whole screen is very fluctuating.
It might be the connection problem from your side.
No, everything was fine. It's just rehearsal. Oh my God.
Okay, you can restart again. I mean, reshare the screen. Maybe it can solve the issue.
I can't see anything on my screen actually. I don't know why this problem happened.
Okay, let me see. I can ask the technical department if they can do anything, but looks like everything is running smoothly from our side.
But I can't even see like my screen.
Okay.
The screen that I shared is very fluctuating. Oh my God.
Okay. What about the? Let's try with the. Let's say the other presenters. If they have the same problem, it is.
Yes, I think so. It would be better.
Yeah. Okay.
Okay.
I would
Thank you
like
so much.
to. It's okay. I would like to ask for any reason, I would like to ask the second presenter and just to check if there's any problem with the system. So then we will return to your presentation.
Okay.
The second one is the effect of auxiliary acceptance on online-based sensitized solar cells, and Dr. Arsalan will present. So I would like to invite you, Dr. Arsalan, to start the presentation. At the same time, we can check if there is any problem from our side or from the first presenter. So would you start your presentation, Dr. Arsalan? Okay, the second presentation I see is Dr. Arsalan. Are you here in the meeting? Okay, looks like the second one is not ready, or they have not joined. The other one, the third one you can try is Mr. Çelikdemir. Are you ready for the presentation?
Yes, of course.
Okay, very nice. Let's start with you. And okay, here we have the third one, a new methodological approach.
Yes.
Okay, no, just we are going to share. If you can share, then we can refer to the first one. Just share your screen. I want to see if there's a problem with you. Okay. Yeah. Okay. Okay. Do you have any problem with presentation or no?
Okay.
Okay. So Rana, I see there is no problem with the system. I mean, with the session. It might be your problem. As you say, there is fluctuation in the screen. So I'm going to ask you again, please share the screen. And let's see what you have in the presentation. If you have any recorded video, you can run that one, because we have to go one by one, because every presentation is set for the specified time. So Dr. Arsalan, thank you very much for sharing. We see that there's no problem with this one. So I am going again ask Rana to share the screen. And let's see, this time, I hope your problem has been solved. Rana, would you please share your screen? Okay, I think she is not online now. Mrs. Rana, can you hear my voice? Okay, you can hear, but we can't hear you. No, you can't. Okay. Looks like, Rana, you missed the connection, right? Okay, we don't have any other option because Rana was here, but now I can't hear. And okay, so let's go to the second one. And yeah, Rana, I am just waiting for you for, let's say, the last time, because the stuff are set for you now. And it looks like you have the problem. Okay, the second presentation, that we have to go to the second one. And this is Dr. Arsalan. Are you ready for presentation? Can you hear me?
I hear.
Okay, Dr. Bashar, so I can see you. You can start your presentation if you can share your screen. Okay. Okay, Mr. Hassan, if you can hear me, I can't hear you. Now we can start your presentation. Looks like Rana is not online anyway.
Okay.
Okay. She's not here. Please move. Okay. We're going to the second one. Okay. I have a message from the technical department. Okay. Mr. Hassan, please start your presentation.
Hi, everyone. My name is Barış Seçkin Arslan. I am doing postdoctoral research at Sakarya University. I am working as a scholar in the Scientific and Technological Research Council of Turkey project. I will present our work entitled Effect of Auxiliary Acceptors on Quinoline-based Sensitized Solar Cells. Today, the overall majority of the world's energy needs are provided by fossil fuels such as coal, oil, and natural gas. However, fossil fuels are non-renewable energy sources and have caused global environmental problems. Among the various renewable energy sources, solar energy is the largest source of clean energy and therefore replace the dependence of world energy needs on fossil fuels. For example, using less than 0.02% of solar energy would satisfy our present energy needs. The majority of commercially used photovoltaic panels are based on silicon. Metal-free organic dye sensitized solar cells have low cost, ease of production, environmental friendliness, a high molar absorptivity, easily adjustable power conversion efficiency. Thanks to these advantages, it has attracted attention as an alternative to silicon solar cells. Conventional DSSCs typically contain 5 components. 1, a photoanode containing a conductive substrate. 2, a mesoporous semiconductor metal oxide film. 3, a sensitizer. 4, an electrolyte. And 5, a catalyst coated counterelectrode such as platinum. The molecular structure of dyes used as sensitizer is one of the main factors that depend on the photovoltaic performance of DSSCs. A traditional organic dye is in the form of a donor pi-bridge acceptor, and the induced electron is transported from the donor to the acceptor by intramolecular charge transfer. The main component of sensitizers is aromatic pi-bridge, which affects absorption capacity of the molecule and processes the most. It has been found that pi-bridges with planar and fused conjugated systems increase photovoltaic performance by wide absorption in the visible radiation region. Many compounds containing various p-bridges such as dibenzonafthridine, an unrelated perylene, phenanthocarbazole, anthracene, phenothiazine, quinoline, tryptophan derivatives, phenolane, furan, were synthesized and used in DSSCs. In most DPA dyes, triphenylamine, carbazole, or diphenylamine electron-rich groups are used as electron-donating groups, and carboxylic acid or cyanoacrylic acid electron-withdrawing groups are used as acceptor-anchoring group. The strong ester bond formed between carboxyl group and titanium dioxide surface improves electron conduction. Zhu et al. Developed an efficient and stable new type of organic sensitizer in the DAPA structure by adding an electron withdrawing group to act as an auxiliary acceptor into the pi bridge of the DAPA structure. In recent years, low bandgap electron withdrawing moieties such as benzothiazole, benzotriazole, quinoxaline, phthalimide, decatoprolol have been introduced between the pi bridge and electron donor, and DAPA dyes have been obtained. It was confirmed that the DAPA system increased the energy conversion efficiency and photostability of the DSSCs. In this work, we sensitized 2 dyes containing diphenylamine as donor, benzothiazole or N-ethylhexylbenzotriazole as auxiliary acceptor, quinoline as pi bridge, and cyanoacrylic acid as anchoring group. We compare power conversion efficiencies of the DSSCs when auxiliary acceptors are introduction to the structure of the dyes. The molecular structures of the dyes we synthesized are shown in the figure. As can be seen, the structures are the same except for the auxiliary acceptor group, BIM1 and BIM2 dyes, both in the APA structure. The total synthesis of dyes BIM1 and BIM2 is shown in scheme. Acetylation of commercially available for bromaniline followed by Wills-Meyer reaction and the nucleophilic substitution reaction gave compound 3 to form the pi bridge of the dyes. This compound was converted to the boronic acid ester for use in coupling reactions to give compound 4. Starting from orthophenyldiamine, auxiliary acceptors were synthesized separately. Then 7 and 11 compounds were obtained, respectively by these compounds and the palladium catalyzed Backwald-Hartwig cross-coupling reaction of diphenylamine. Subsequently, by Suzuki-Miore coupling reaction of compound 4 with compounds 7 and 11, compounds 12 and 13 were obtained, respectively. Finally, dyes BIM1 and BIM2 were synthesized by Novak-Nagel condensation. The absorption wavelengths lambda max for dyes BIM1 and BIM2 are 476 and 400 nanometers. Remarkable redshifts observed for dyes BIM1 and BIM2 can be attributed to the presence of stranger electron withdrawing benzothiazole and N-ethylhexyl benzotriazole moieties on the dyes. The power conversion efficiency DSSCs based on BIM1 is much higher than that of BIM2 due to its broader absorption spectrum. When compared to 5A, 5B on DSSCs in DPI structures in our previously study, it is seen that BIM1 and BIM2 based on DSSCs have both redshifted absorption wavelengths and higher power conversion efficiency. Conclusion, the DSSCs based on the dye bearing benzothiazole show the PCE of 5.21%, which is better than that of 3.65% for the dye with N-ethylhexyl benzotriazole. As a result, the insertion of a proper auxiliary acceptor to the sensitizer is an effective way to enhance the photovoltaic performance of the DSSCs. Thank you for attention.
Thank you, Dr. Arslan, for the nice presentation. We have time actually for questions, if there's any, from the respected audiences. Any questions? So I have a very quick question. Why did you select these specific auxiliary acceptors for this research? Can you, select the or specify other types of the acceptors for this sensitizing, or there is a specific reason behind it? So you can explain.
Known.
Okay.
They are known to be good auxiliary acceptors.
Mm-hmm. So they are widely used. You mean that is the reason you selected them?
Yes.
Okay. Okay. Any other question from the audiences? It was a nice presentation. The importance of the solar energy, especially for Turkey. Thank you for the sharing of your results and your study. We appreciate it. If we don't have any other question, I can't see any question in QA. So it means that we can, again, thank you, and go to the third one. Thank you. The third presentation is about the hydroelectric power. So a new methodological approach for the techno-economic analysis of hydroelectric power plants in Turkey by Mr. Çelik Demir. Are you ready for presentation?
Yes.
Okay, perfect. Okay, floor is yours, and you can start your presentation. Again, you have around 14 minutes for the presentation. Thank you.
Yes. Okay. Can you see my
yes, we can see. Yes, you can go ahead.
Hello, Mr. Chairman, ladies and gentlemen. Thanks for coming to my presentation. Before I start my presentation, let me introduce myself. I am Soner Çelikdemir. I am working as a lecturer at Bilimler University. At the same time, I continue my doctorate education at Prague University. Now I would like to brief you on the context of our study. The name of study any methodological approach for the techno-economic analysis of hydroelectric power plants in Turkey. Our presentation belongs purpose to study bio study Turkey's hydroelectric power plant potential, techno-economic analysis, results and discussions, contributions of this study and feature. So first, I would like to talk about the purpose of the study. In this study, investment cost of hydroelectric power plants in Turkey are analyzed more realistically. For this, any methodological approach has been proposed. Equation model with 4 terms and 7 parameters is purposed for analysis. Archimedes optimization algorithm is used to determine education parameters. The study is handled in 3 stages. In the first stage, Turkey's 25 city regions are divided into 7 groups according to precipitation and elevation values. In the second stage, separate equation parameters are determined for each group using a total of 6 to 7 hydroelectric power plant data. In the final stage, sensitivity analysis of the equation model developed is performed and the effect of the power, heat, and flow parameters of hydroelectric power plant on cost is shown. It performs and the effective power. In this way, a different methodological approach was applied. The importance of this study is that it is a first in the literature because there is no such study in the literature. There are several reasons for these purposes. One of them is why did we do this study? Because the importance of hydroelectric power plant source, and in the way emphasize the importance of techno-economic analysis of renewable power plants. Current studies are unrealistic. In that electromechanical costs were used in the studies or some parameters were neglected or the classification was made according to the turbine type. Because electromechanical costs do not cover the total cost. In this way, it can give misleading information. In this way, to emphasize the importance of techno-economic analysis of renewable power plants. That's helping to fill the gap in the literature. So another reason for our purposes why it is hit hydroelectric power plant in Turkey, because Turkey is in a position reaching hydroelectric power plant. Turkey has many rivers. There are also 25 river basins. The energy potential of these basins is high. In these basins, the hydroelectric energy potential is expressed by the drop to sea level and the average. Flow rate converted into energy without loss. In this case, when the current basins of our country are examined, the gross theoretical hydroelectric potential value of our country is 433 billion kilowatt hour year. The technical accessible potential value is 216 billion kilowatt hour year. And the economically developed potential value is 158 billion. As of the end of December 2020, Turkey's total installed power of license hydroelectric power plant is 30.97 megawatt. Ratios regions of license installed power value according to energy source. It consists of 47.29% fossil-based energy source, 32.31% heat hydroelectric power plant, and 9% wind power plant, and 6% solar power plant. So the geography of Turkey consists of 25 river basins. When these basins are examined, although they have different river branch, the precipitation and altitude values of some basins of similarity. Taking this similarity into account, river basins are grouped. It is generally represented by in the presentation equation. In this case, it can be done that Turkey is calculated according to the river basin altitude and annual precipitation rate. In this way, river basins with close altitude and annual precipitation values are included in the same classification. In this case, there are 7 different classes. The cost equation parameters were calculated for each of these classes. In the table, values are given as a result of the calculations made. In this case, the obtained results were compared with the literature results. In this study, O'Gahn made a classification according to the Turbine. The maximum percent error values were found with 23% for the platform and branches turbine, and 22% for the Kaplan turbine. Mean error values were found at 9 and 11 and 9 respectively. Likewise, Kawasani found the maximum percent error values to be 17% for the platform turbine, and 16% for the branch turbine, and 22% for the Kaplan turbine. Filho, on the other hand, found the maximum percent error values as 50% and the mean error value as 21 in his study. In our study, we found the maximum percent error value at 16%, and the mean error value as 3. So, in this section, sensitive analysis is performed to see the effects of parameters values on cost in the proposed equation model. For this, the parameters in the equation model are examined respectively while performing the sensitive analysis. When the graphs of the sensitive analysis are examined, it is found that the installed power value on the cost in the 20, 30, 40, 50 Bayesian classes is more effective than other Bayesian classes. Likewise, it is in that the flow rate on the cost is more effective in the first, second, and 70 Bayesian classes than in other Bayesian classes. With this study, the cost of a hydroelectric power plant to be installed in any basin of Turkey can be predicted with high accuracy using the proposed equation model. Likewise, the cost of hydroelectric power plant to be established in different currents with the characteristics of Turkey's basin classes can be predicted with the proposed equation model. In determining the equation model parameters, the investment cost information of hydroelectric power plant was taken in the account. In this way, investment cost can be predicted with high accuracy using the proposed equation model. Investment cost of hydroelectric power plant in the country can be predicted with high accuracy. This way, investment in renewable power plants will increase. The number of hydroelectric power plants data in the data pool can be increased, and parameters used in the proposed cost equations can be added or subtract, and different optimization method can be used. Different methodological approach can be developed, and more tailored cost analysis can be made. Yes. Thank you for listening to me. If you have questions, I can get it. And my contact information is. Thank you.
Okay, thank you, Mr. Çekdemir, for the nice presentation. It's a very critical subject for the country, the hydro. So first, I would ask the audiences if there's any question. You have time for a couple of questions, and you can write in QA, and then I will read. But I see one question, which is about the percentage error rates. And the question is, if this calculated value for about 90.96% reasonable value somehow, isn't it high or is it reasonable? So would you please explain about this, the error rate in your calculations?
We found the maximum percent error value at 16%, and mean error value at 3. Indicate the obtained results are compared with the literature results, the base result.
Okay. So the other question, is there any other question? If not, I'm going to ask you another quick question from you. And my question is about the assessment of the model. The model that you have improved in this study, is it specifically for Turkey, or you can apply this model for estimating the cost for other plants in other parts of the world? So, I mean, the conditions for developing and improving the model. So if it is only for Turkey, or it can be widely used in other regions also?
We can improve the economic techno equation model. I can't answer the questions.
It's okay. Yeah. So you can improve it. You can let's say modify the model for other countries also. That is my question.
Yes. Yes.
It is possible. Okay. Very nice. And so I don't see any other question in the QA section and the other. This means that, you know, we can move to the next presentation. Mr. Çekdemir, again, thank you for the nice presentation. And now I'm going to introduce the fourth presentation, which is again another important topic of renewable, especially for Turkey. And it is about the extreme wind and risk analysis in Turkey for wind energy applications. So this work will be presented by Mr. Kara, if I pronounced correct. So are you ready?
Yes, I am ready now.
Okay, perfect. Hello. We can hear you clearly. So again, we have 15 minutes for your presentation.
Okay.
And the floor is yours. You can share the screen and we are listening to your presentation.
Okay. I will share my... Yes. Okay, now. Sorry.
It's okay.
This prize is missed. Hello from Istanbul to all attendants. I am Tolga Kara. I am a PhD student in atmospheric sciences at Istanbul Technical University.
Tolga, Mr. Tolga, we don't have your screen.
Ah,
still.
Really?
Yeah, I think you have to try again.
Okay.
It might, yeah. Looks like something is coming up, but not
Now,
yet.
Maybe.
No. Still we can see.
One. Okay, I will try again.
Yeah, share screen. Let's.
Now,
Unfortunately, I see myself again.
How could it be? Because the sharing options are available, and I am sharing my screen, and there is a it says the stop sharing.
It might be from the previous presenter. Maybe they didn't stop presenting.
I don't know.
It might be the problem, but I will ask the. Okay.
Because it shows you are sharing the screen. Yeah, it says the screen. I can see that you are sharing the screen, but you can't see my screen.
Yeah.
It's interesting.
So I believe he uses two screens and the presentation on the other screen.
Okay, maybe there is a.
Are you connecting with one system or two?
Close tab. Participant can now see your screen. My Zoom is closed. I am on the browser. I can share. But okay, Sertaç says he uses the two screen, but I just use my laptop screen. I just one screen.
Okay, no worries. Let me ask the technical department to help you for the issue. Did you send the presentation to us before? You can share it.
I was sent with the mail. I have some changing on that, but the whole thing is same in there.
So they say that you need to select the presentation software then, and not the Zoom.
The selection of browsers can lead this problem. I use Brave browser, maybe Chrome.
Okay, Mr. Tolga, we didn't solve the problem, no? Please click the chat share button. Okay, did you see the share button at the bottom of the screen? There is a green share screen.
Okay.
Click on the share screen. You should be able to present, to share the screen. Did you check this green button at the bottom of the page? Share screen?
I tried to use another application window.
There is no need because you are in the Zoom. If you click on this share screen, then it should work.
Okay, I use share screen then.
Yeah, just close other applications that you have.
Okay.
And just click on the share screen at the bottom without other applications, and let's see.
I use this Zoom from the browser because the system does not allow me enter the Zoom desktop Zoom. Maybe that's the problem from me.
I see. And I don't have control on your screening.
Okay, hold it. I will try to join with the desktop again, but it does not allow to me.
Okay.
Okay.
Let's try this one. Yes, we have time. We have 12 minutes. We can, share. We can have enough time. Okay. You are a panelist. This means that we can share.
Okay. Now I am okay. Let me. I join with the desktop Zoom. Now I try to
Hello, Mr. Tolga. Can you hear me?
Yes.
I'm Technical Office from TÜBA, Turkish Academy of Science. Now we will control your desktop, remote control, and don't touch anything, only accept our request, okay? It will now seen on your screen, okay?
Okay, okay.
Now, can you click on share screen again?
Sure.
Yes, we
Right.
can.
Wait a moment. Okay. Now, can you accept our request?
I approve that.
Right. You are using PDF or?
It's a PowerPoint.
Yes. Now, can you click on F5 over and over?
Is the slides are changing now?
No, no, not yet.
Okay. I am passing the slide to slide now.
Do you have two screen or one screen? You have one screen, yes?
Yeah, I just use my laptop screen. So just one screen.
All right. So is there something on your... Now, can you move back and forth?
Yes.
Right, now we can see like this. Now, this time we will watch like this, okay? In case of not wasting a lot of time.
Okay, I won't do the full screen.
Can you try full screen?
Oh, okay. How can I do that?
If it doesn't work, no need to worry. You can continue like this, okay? We see it very nice right now.
Okay, I couldn't
Okay, now you
find
can move
making
forward.
full.
Okay, let's continue with this format. It's okay.
Can you see clearly the?
Yes, we can see. We cannot.
Okay.
If we cannot have it full screen, this is acceptable.
Okay.
Finally, we saw. Thank you for your help from the academy. And there is no need for panic. You have 10 minutes, 9 minutes. So this will be a good presentation. We are listening to presentation. Please go ahead.
Okay.
And I think you can skip the first introduction parts and go to the work itself. So
okay, tamam. Maybe I have some points. Okay, in Turkey, maybe this I can mention this figure. I take this figure from the Turkish Wind Energy Association's web application, which shows the wind energy applications distribution map in Turkey. The western part of the Turkey is really windy, and there is a high number of the wind energy application investments are made. You can see that the yellow circles means the wind farms. So there is the other parts of the Turkey also have the wind energy, wind farms. Okay, I will pass here. Also, I can mention here also the provinces of Turkey, the Izmir, Balıkesir, Çanakkale, and Manisa has the higher installed wind capacity in Turkey. Izmir is close to nearly 20% of the installed wind capacity. So Izmir is the Aegean region in Turkey. Balıkesir and Çanakkale is located in Marmara region. Okay. The extreme wind is defined in this study as the extreme 10 minutes average wind speed with a return period of 50 years, which is also defined in the International Electrotechnical Commission. It is the standards of the wind turbine design also. This is the typical wind turbine power curve. The cut-ins between the cut-in speed and rated speed, there is a partial wind loads on the wind turbine components. Rated speed and between the rated speed and cut-out speed, there is a full load operations, we can say. The cut-in speed is where the wind turbine blades are started to rotation. After the rated speed, the power production is steady because the load, full load operation, that can be, it's a mechanical availability. So if the wind speeds exceeds or reach to cut-out speed, there is a need to shut down the wind turbine or making some wind turbine control techniques to diminish to damage of that mechanical load to the wind turbine. Okay. There is for the wind turbine design for the specific areas, there is some international standards as I mentioned. Wind turbines are designed within the 3 specific classes according to these standards. So those are characterized by the wind regime and expected mechanical loadings. The reference wind speeds are here, as I mentioned, the 50 years of return period. These are the design criteria of different wind sites. If there is the mean wind speeds is around to 10 meters per second, and its reference wind speed is the 50 meters per second. It's the 5 times bigger than the annual mean wind speed. These snapshots from the New European Wind Atlas web application, you can examine this website from the reference link. It is publicly available. We were the part of this project as ITÜ from Turkey. The data used in this work was taken from the database of the New European Wind Atlas project. The publicly available mesoscale data in the atlas covers Europe with the special resolution of 2 or 3 kilometers. The time series of the average 10 minutes wind speeds over the 2016 and 17 were used for the 50-year winds analysis further sections. These calculations are applied for the regions and selected provinces of Turkey as a study areas. I forget to track the time. If you can, how much time I remain? I will be faster.
I see here, you don't have more than 4 minutes.
4 minutes?
Yeah, 3 to 4 minutes.
Okay, I will take my motor. These are the methods that we use in this study. Extreme wind speed model, annual maximum method, and peak over threshold value method. These are the equations from the IAC standards documents. The extreme wind speed model is included in that standards. So we used these equations from that document. This is basically based on the reference wind speeds. The second one, the annual maximum method, using the Gumbel distribution is a good way to model the extremes of the natural phenomena, especially floods and winds. So these calculations made for the annual maximum method by using the Gumbel distribution. The risk calculation is use this basic equation, which is the estimating the probability of occurrence of the return period during the operational lifetime of the wind turbine. The last method is peak over threshold method, is based on the generalized Pareto distribution. We use this distribution for the determine the threshold value. We used our software's functions in this study. To coming to results of this study, I used to red lines for the where the installed wind capacity is higher in Turkey. The Hatay is the one of them. So the maximum wind speeds in the our data set is nearly 30 meters per second in 2016 and nearly 28 meters per second in 2017. So after the calculations based on that, I showed the equation, the maximum extreme wind speed with the 50 years return period is 30.24 meters per second, which is below the IAC standards wind turbine class 3, because it's nearly 37.5. So the analysis from this perspective for this model. So Balıkesir and Çanakkale is the another cities with the high wind capacity. So these are also does not close to that wind turbine class standards. So selection of the wind turbine is based on these calculations. We can use the third class while deciding to turbine selection. So, okay, I will pass here because I have less time. Using the Gumbel distribution, we use the graphical method to determine the Gumbel's distribution parameters by using our software. This is a regression line for the extreme.
I'm sorry
yeah.
for interrupting. You know, time is over. Let's say
Oh.
in 1 minute.
Okay.
If there's any question,
I have
because yes.
Okay, I will use that 1 minute because I have a full table to understand the whole concept.
Okay, go ahead there.
It's better to see that.
Yes, please.
Okay, this is the extreme wind values of the selected provinces for the 50 years return period based on the different methods. These are the POT is peak over threshold method. AMM is the annual maximum method. EWVM the extreme wind method. So we can see here all the T's are for the POT does not exceed the wind turbine class 3. But if we examine the AAM method, there is one and Samsung is exceed that wind turbine class 3. So if we choose the wind turbine according to these calculations, for the one and Samsung, we need to use the wind turbine class 2. Yeah. There is a huge number of criteria to selection of wind turbine, of course, but the small perspective to and to understand basically to calculations I mentioned about that.
Okay, thank you.
Of course, there is lots of
Tolga, the time is over. No,
okay,
yes.
okay.
Yeah, so thank you for the presentation. It is very interesting. Unfortunately, we don't have time for questions, but very small question. Question I want to ask. You have developed this model to select the wind turbines, right? How much this model can be commercialized outside in the market? And let's say if the investors or the people dealing in this sector are interested to use your model or no, how you can, make it widely accepted, or what is the problem if it is not?
In the study, there is some lack of applied information, because we used only 2-year wind data. It is uncertain for the calculations of the extreme winds. There is a need some correction methods, such as the spectral correction method.
I understood. You mean that the data is not enough?
Yeah.
Enough. Okay, very nice. Tolga, it is very
it gives information about the concepts, but we can't exact wordings about these results.
Okay, very nice. Thank you for your effort, and thank you and your colleagues for this nice
I thank
study.
You too.
Thank you very much. And we don't have time, unfortunately. So
I'm upset about that. I have
it's
lots of saying about it.
Yeah, it was a wonderful presentation. Thank you again.
Okay.
And have a good time. Let's move to the
I stopped my share.
Okay, so let's start with the presentation. Again, it's about the wind energy, techno-economic analysis of onshore and offshore wind power plants by Mr. Özdemir. So floor is yours, and you can, but if you just, possibly make it in 10 minutes, because after that we have the first presenter. I am going to give 5-6 minutes to Mrs. Rana to present if you have time. So it would be appreciated if you can just make it in 10 minutes. Mr. Özdemir, are you there?
Yes.
Okay. Floor is yours, please. Go ahead.
Yes.
Okay, you are. It's okay. Nice. Okay, we can see your presentation.
Can you see my?
Yes, nicely. Yeah, go ahead.
Hello, Mr. Chairman, ladies and gentlemen. Thanks for coming to my presentation. Before I start my presentation, let me introduce myself. I am Soner Çelikdemir. I am working as a lecturer at TÜBA University. At the same time, I continue my doctorate education at Pratt University. Now I would like to brief you on the content of our study. The name of our study, techno-economic analysis of onshore and offshore wind power plants. Our presentation flow is purpose of the study, why of the study, onshore and offshore wind power plant, and techno-economic analysis, case study, result and discussions, and feature. First, I would like to talk about the purposes of the study. In this study, an equation model is purposes for...
Mr. Özdemir, one very quick note. If you want to read from the slides, we don't have time. And we have 5-6 minutes. So I would be very happy if you go to the results of the study very fast. No need for the introduction and information. They're nice, but we don't have time because we have 2 other more presentations. Just go to the results of the study. You have maximum 5 minutes to finish and wrap up the presentation.
Yes. In the studies, an equation model is purposes for the first time to estimate the cost of wind power plants by analyzing the investment cost of wind power plant in Turkey. In addition, a case preliminary studies carried out in Ağustos region with the purpose of equation model. The cost of the wind energy farm to be established in the designated area are calculated for different turbine models, and the appropriate turbine model is selected. In addition, an equation model has been developed for the estimation of the cost of offshore wind power plants by analyzing the investment cost of the existing offshore wind power plant in the literature. For the equation model, unlike the literature, distance from the shore and deep parameters are also added. By analyzing the sensitivity of the model, cost changes in different parameters, values are expressed. In the study, a preliminary case study is carried out for different zones in the Bozcaada zone with the purposes of short equation model. The cost for the different turbine models of the wind energy farm to be established in the determined zone has been calculated, and appropriate zone selection has been made. There are several reasons for these purposes. One of them is why did we do...
Mr. Çelikdemir, one more time, I have to mention, we don't have time. And you have 2-3 minutes to go to the results of your study, because we have one more. No need for this introduction, no need for talk about why you are doing this. We want to see the presentation in the result, right? The results of your study. You have maximum 3 minutes.
Okay. In this case, in the first picture, there is a visual of onshore wind power plant. In the second picture, there is a visual of offshore wind power plant. So in the Professor equation model for onshore wind power plant cost installed power, height and rotor diameter parameters were used. In the equation model proposed for offshore wind power plant, distance from the shore and water parameters are also added. Archimedes optimization algorithm is used for the both equation model presentation. In this section, the cost of wind energy farm to establish in Ağustos region has been estimated in the study. 41 turbine models belonging to different plants are examined. According to data obtained, the most suitable model for the wind farm to be established in the region will be Nordic, and 173.3 with the lowest unit energy cost, and the worst model enercon is 82.31 with the highest unit energy cost. In addition, as the hook height increased, the average wind speed value, scalar parameter, capacity factor, and power density value increased. The actual runtime and the amount of energy potential vary according to characteristics of the wind turbine. Offshore wind energy potential were determined using 6 different measurement stations that are in Bolcada and Gökçeada zone on the Aegean coast. The study results for this zone are given in table, taken into account distance of this zone to the shore and deep data. The most suitable model selection has been made for the wind energy farm to establish it in the zone with high energy potential.
Mr. Çekdemir, your time is finished. And if you can just show the last slide for the results, it would be great. Okay.
Of course. The last result of the sensitive analysis study for offshore wind farm are given in figure. In the sensitive analysis in the picture, with the equation in this study, a cost equation is purposed for the first time for onshore wind power plants and contribute to the calculation of cost equation parameters using Archimedes algorithm optimization. In the case study, content for the Abijav region calculations are made.
Okay, Mr. Çekdemir, I am going to thank you for the presentation. I'm sorry that I can't allow to finish the slide because the participants can see the results, and I appreciate your presentation. And if there's any question, you can write to Mr. Çekdemir. At the beginning, we saw the contact information, and so I'm going to thank you, Mr. Çekdemir, again, and sorry for the time limitation. And the last presentation is going to be again about the renewable, and then I'm going to introduce the title, which is Performance Evaluation of Solar Dryer with and without solar photovoltaic heat extraction. And Mr. Tiwari, I see you here, and floor is yours. And it would be great, again, if you can wrap up in 10 minutes, because we have a bit a limit.
Yeah, sure, sir. Sure, sir.
Yeah, okay, thank you very much. And the floor is yours. We're listening.
Yeah. Good evening to all. So my presentation is related to performance evaluation of solar dryer with and without solar photovoltaic heat extraction with my 3 students who got some project from Government of India. So we have implemented, and with the theoretical analysis, we got this paper. So I'm just skipping the background, like the drying used to take energy that may be high grade energy or low grade energy. So our purpose of fabricating this dryer to use the low grade energy, or which is available in the environment freely. So that will support the environment, as well as we can make the system self-sustainable. So this is the experimental setup which already exists, people working on that. So, but it is not self-sustainable because we cannot run it in forced mode. So if you want to extract more moisture content, we have to go for some other alternate. So what we have done, we have connected this dome type greenhouse dryer with the PVT collector. So this is the structure. Here, this is the PV collector. So PV collector, why we have taken? So that the apart from the heat energy, extra heat energy that can be fed to this dryer, we can run the DC fan also. And the beauty of the DC fan is according to solar radiation. For example, if solar radiation is more, we have more evaporation inside the dome. So we have to take out quickly from the dome. Otherwise, what will happen? It will accumulate, and it will reduce the further moisture evaporation. So due to the PV cell, if radiation is more, it used to produce more electricity. See, if you have more electricity, then fan rotation will be more and it will take out the moisture content at faster rate. So it is some kind of self-sustainable system. According to moisture, it can adjust itself. So for that, we have done some modeling. First of all, we have made equation. We have taken equation for this dome structure. Then we have made equation for this PVT collector and connected both of them. And finally, we got the results in terms of different temperatures. And from different temperatures, we can calculate other energy parameters. So in case one, thermal modeling for solar dryer. So we have done energy balance equation. Then energy balance equation for air inside the dryer. Then energy balance equation on the product. Then energy balance on floor, mass balance equation. We have 5 equations we can solve by the help of MATLAB program. And to solve this equation, we required the different heat transfer coefficient, which can be further calculated by the help of different correlations available in the literature. So now we can calculate the heat transfer coefficient. We can put the values and we can get the solutions. So for moisture ratio, we have different correlations for different crop like banana, chili. We have different models. So we have taken 3 of the such models, and we compared how the behavior moisture evaporation is going on. So then in case 2, we have taken the dome structure as well as we connected with the PVT system, PVT air collector. So for PVT air collector, this is the energy balance equation. Finally, this is equation for cell temperature. Then in the same way, we have got the equation for the temperature for the exit temperature from the air collector. So this is first order differential equation we have solved again by the help of MATLAB programming, and further we can get the different energy parameters. So this is the temperature variation inside the dryer with solar radiation. So this is the input energy which we have taken according to our climatic condition. Presently, I'm in Shivnadar University in India. So we have taken the data from here. So finally, after solving the results, theoretically, we got different temperatures like greenhouse temperature, then ambient temperature we have already taken. Then the floor temperature, the product temperature, all temperatures we got here. And what we find, we got around 10 to 15 degree average temperature difference from the ambient temperature when we have taken just dome structure. Then moisture ratio we have calculated, and we got for cotton, banana, and chili. So if you see that banana drying takes less time compared to other 2. Now we have compared with PVT, which we have connected, and we got further around average 15 degree temperature enhancement. So effectively, if we compared with ambient temperature, the temperature difference around plus 30 degree average. And also we have got very interesting result. When we have seen the cell efficiency as the temperature, ambient temperature or cell temperature used to increase, the cell efficiency used to decrease. Now this is the variation of temperature air inside the dryer between greenhouse and PVT integrated greenhouse dryer. Then this is the variation of moisture ratio over time different crops in greenhouse dryer and PVT integrated greenhouse dryer. For all 3 crops, what we found that in all cases we got better drying, or we have increased drying rate. So from the result and discussion, we can conclude or we found that the chili drying needs 2 to 3 days for complete drying compared to 1 day for banana. And in PVT integrated dryer, all 3 crops showed moisture ratio decrement slope increased, which may help in fast drying. Then application of PVT air collector makes the system self-sustainable for working under force mode. And also further, we want to extend in dome, we are going to put the PCM material, phase change material, so that the drying can be used in nighttime also when solar radiation is not available. So these are the references, and thank you.
Thank you, Mr. Tiwari. It was very interesting presentation with the experimental data you employed. And also you mentioned about the phase change material, because we had a presentation today about using a PCM for this type of the systems. Very interesting study. I really appreciate your report and your study. Unfortunately, we don't have time for.
Thank you so much for inviting.
For questions. No, it was great. We thank you, and we hope you to have in the next events that we will have hopefully. And I thank you again. So if there's any question from respected audiences, you can directly write to Mr. Tiwari for this nice work. So at the end of the session, I just try to have 5-6 minutes, actually 5 minutes to the first presenter, Mr. Rana. Are you here, Rana? Okay, I see you are here. Can you hear me?
Hello.
Hello, Rana. We can hear you. Can you share your slides and just wrap up in 5 minutes? We have. If you let's see, can we see your slides? Rana, can you hear me? Okay, we heard you first time, but after that we couldn't hear. Can you hear me one more time? Okay, so what I'm trying to do here, because Rana, unfortunately, we can't have your voice even. So this is what I'm doing, Rana. I'm going to share the screen for the presentation that Rana had. So can you see my screen now? Everybody? Okay. No? Okay, let's see, share again. Okay, you have the presentation here. Let me just bring it here. Okay, the subject was about potential use of renewable energy for rural electrification in Pakistan by incorporating blockchain technology. And you see the slides here because she couldn't be able to present. I'm just sharing the slides, what she did in the study. You see the outlooks and the objectives of the study. Of course, about the introduction, talking about renewable energy importance. And they are developing a blockchain technology in Pakistan energy sector and provide an alternative way of energy distribution, mostly for the distant areas with the help of small setups. Blockchain technology is explained here in this slide, you see, by some examples. Blockchain application scenarios in the energy sector is seen here. And we have the case study applying the system in Pakistan, implementation perspective, and recommendations, available scenarios for Pakistan. Resources potential are seen here. Household distributed power generation, digitalization of energy market system model. Unfortunately, we don't have time to discuss. Actually, time is over for this. I was expecting to have Rana here for a brief and short presentation. We have the conclusion and policy implications of the study here, main constraints for blockchain integration. I believe it's talking about the constraints in Pakistan for applying this model management barriers and others. So Rana, this is what I could. This is what I could to just share your slides, and I think the time is over. Yes, I have no extra time, and I'm going to thank everyone for participating in this meeting. And this session had 6 presentations. Now we are going to have the other session after this, as you can see from the program. One more time, I'm going to thank you all for joining us in this session, and wish you the best, and hope to see you again in our next events. Thank you.
Dr. Rana, do you have any questions?
My question is is anybody hear my presentation? Because I gave my whole presentation and due to the poor connection, I can't even see any review and I have just 5 minutes to complete. So I'm blank.
Unfortunately, we couldn't hear you, so your session is over. We are sorry for that.
But what about my presentation? Should I have to arrange it again or what I have to do? Like I prepared and
I think your internet connection is poor. Maybe we should
hello?
contact with your, chair.
If the moderator or is here, I can deliver it again if he wants to.
Let me check, please, Dr. Rana.
Yeah, thank you so much. Please check it. I'm actually give this presentation now.
All right. Let me check, Dr. Rana.
Okay. Thank you so much.
Dr. Rana, can you hear me?
Hello.
Unfortunately, we cannot accept your offer.
Yes, I can hear you.
Because we have a tight schedule, So your session is over. We are sorry for that.
And excuse me a moment, please. I just want to ask either, I don't even know either they heard my presentation or not. If they heard, then it's okay.
No,
if
we cannot hear you because you have a poor internet connection as far as we can see. So the chair read your presentation. So as far as we see what you have done so far on the presentation. Okay. So as you know, we have a tight schedule. Unfortunately, we cannot allow a place for you.
Okay,
Dr. Rana, thank you for attendance.
Okay, thank you.
Could you please confirm whether you can hear me?
Hello, I confirm that I'm hearing
Okay,
you.
thank you. Thank you, Paolo. I think it is time to start. Good afternoon all, and welcome to this session, Microgrid and Smart Grids. Today we have excellent presentations, actually 6 presentations we have today. Before starting, I would like to take this opportunity to hope all you are okay and staying safe, especially during this unusual time. And hopefully next year, or I don't know when will be the next edition of this conference, I hope we will meet physically, and it will be more attractive for all presenters and the audience as well. Now, today, as I told you, we have 6 presentations. The first presentations will be, the title is The Lightweight Deep Learning Model for Smart Grid Stability Prediction, will be presented by Ferhat Uçar from Fırat University, Faculty of Technology, Electrical and Electronics Engineering, Elazığ, Turkey. Ferhat? Can you hear me? I think your mic is off. Could you please turn on your mic? Dear Ferhat, can you hear me? Dear Ferhat? Okay, he said he cannot hear anything. I don't know. I think others, could you please confirm whether you can hear me, or the problem only from his own computer? Dear host, could you please confirm whether you can hear me? Okay. Dear Ferhat, are you able to solve the problem, or we can move the next one, because I don't want to spend time. We can return you when you are okay.
Dr. Serhaç Bayhan, can you hear me?
Yeah, I can hear you.
If there is a technical problem, maybe we can pass on to the other presenter.
Okay.
Okay, thank you.
Now let's move to next presentation. A smart monitoring and protection system design using visible light communication for grid integration of microgrids. I don't know who is going to present this one, because...
Dear Chairman.
Okay.
Can you hear me?
Yeah, I can hear you.
Okay. If you approve, I make this presentation.
Okay. Are you one of the others? No, I cannot see your name.
I see, but we are studied at same laboratory, and you correctly say, Alper, you can.
I don't know. Okay, you can present, but I would like to ask host whether he can or not on behalf of the others. Could you please confirm?
Confirm.
I think you can present. You can start. Please share your presentation, and you will have maximum 12 minutes, okay, for your presentation.
Thank you. Thank you. Is it shown?
Yes, we can see. Please go ahead.
Okay, thank you. Thank you. Sorry for everything. Hello, everyone. My name is Alper Yılmaz, and I'm a PhD candidate at Bursa Technical University. I'm studying at the Renewable Energy and Smart Grids Laboratory with my supervisor, Gökhan Bayrak, and the other researchers. The paper I will be presenting is a smart monitoring and protection system design using visible light communication for grid integration of microgrids. And as is shown in Renewable Energy and Smart Grid Laboratory at Bursa Technical University, our studies mostly offer solution for the integration of renewable energy sources into the grid. The test systems and components we use in our work are seen in this figure: PV systems, our test systems, power quality disturbance, data equation systems, fuel cell systems, and our interfaces are shown in these figures. With these test systems, it is possible to obtain data to be used in studies such as classification of power quality events, islanding mode detection, and real-time studies. An outline of my presentation: first, I will talk about introduction, and then I will explain our proposed method and its background. And finally, I will give the results, and I will finish the presentation with the conclusion. And different types of protections are used to protect the devices in the electrical power system. The task of this protection unit is to prevent damage to the device or the person by removing the faulty or overloaded devices or parts of systems in the case. The conditions that must be met in the protection system are selectivity, precision, reliability, and speed. In order to fulfill all these features, malfunction situations that may occur and devices that will protect against these conditions should be used. And recently, new protection systems are needed to the problems of the safety equipment in the power systems in terms of reliability and speed, and the needs of the developing smart grid systems. In recent years, especially with the development of the smart grid concept, the visible light communication system and VLC system has come to the fore with its reliability, significantly higher data rate, and new generation technology that consumes less bandwidth in data transmission. And highlight of this paper: in this paper, we improve a smart communication substructure for microgrid systems by using the VLC system instead of radio frequency RF systems or power line communication systems. The main contribution of the paper are summarized as follows. We propose a VLC transceiver system that uses 8 IPPM technique to provide the data transmission. We describe a data mapping method for fault condition, voltage, and current amplitudes. In our scenario, the fault detection is carried out the transmitter side. The type of fault is transmitted to the receiver by using a data package which consists of 8 bits for fault conditions, which are defined in IEEE 929-200 as over voltage protection, under voltage protection, over frequency protection, and under frequency protection, are registered a package by using an improved fault coding method. 4 code streams are generated to define the type of fault. We designed all monitoring system using our communication system instead of wireless system standards. This case provides flexibility to update the communication substructure for future grid systems. And in this study, grid voltage and frequency information were obtained in real time by VLC using the LabVIEW software interface developed based on FPGA using a Microgrid processor. The voltage and frequency that obtained was experimentally performed with the modulator and demodulator designed based on VLC. Then the signals to be transmitted to circuit breaker were checked with the developed VLC-based system in order to be able to leave a system connect to the grid in voltage and frequency imbalances. Thus, an innovative method that enables a communication override, which prevents switching and data losses, has been developed. Thanks to the structure, a technological system has been proposed that can be applied in practice, especially for innovative protection methods required for smart grids. And background, VLC, the visible light communication, is a promising technology for wireless optical communication systems. Compared with radio frequency communication, the VLC systems cannot affect from electromagnetic interface. Thanks to this characteristic, the VLC systems are very appropriate for electrical substation and electrical genetic systems where include intense electromagnetic radiation. And proposed method. In the test system, the output of PV system is connected to the grid via a full bridge inverter. Inverter output is filtered, it's connected to the grid via the circuit breaker. And there is a parallel RLC load in here at the PCC, point of common coupling point. By using the voltage information at the point of common coupling at the PCC point, the protection process is carried out with the proposed method. And VLC system block diagram has shown in this figure. The voltage signal from the grid is read from the analog input of the microprocessor and comes to the modulator block via the lab view interface. The modulation and demodulation of the signal is created with the lines of code written in the VHDL language. The IP generator block was used in the LabVIEW FPGA part to add the generated code to the interface and upload it to the Mario card with block diagrams. Invisible light communication in VLC, LEDs are used as transmitter because of the low cost and high energy. On the receiving side, photosensitive photodiodes are used and regulator circuits are here, these systems. Our experimental test system has shown in this figure. The software development system, we use LabVIEW and VLC electronic circuits as shown in this figure. It has a regulator transmitter circuit using LED and receiver circuit using photodiode as shown in this figure. And measurement tools has shown in this figure, and you can see transmitted and received data same. And in this study, 4 conditions seen in the presentation for protection are discussed. First one is over voltage protection, OVP. Second one, over frequency protection. And third one, under voltage protection. And finally, under frequency protection. There are concept of protection shame. The system tolerance, negative or positive 10% has determined this study. Program interface has shown in this figure. And over voltage protection. For OVP condition, when the voltage value exceeds the specified limit value, IEEE 200 standards, it's clearly seen that LabVIEW interface has shown in this figure that the breaker opens, the voltage value exceeds the specified value, threshold value. And during the operation of the system, the amplitude value of the grid voltage at the operation status of the circuit breaker are given in table. The grid amplitude value exists the limitation value. The circuit breaker goes to logic 1, and the circuit breaker properly opened and detect the proposed method detected this condition properly. And over frequency protection, the LabVIEW interface is shown in the figure for this case has shown, and the frequency exceeds the specified limit value, the circuit breakers opened, and this fault detected properly again. In the graph, the part where the circuit breaker is activated as a result of 10% increase in the grid frequency. Grid frequency chosen in this study is 50 Hz, and it goes to 56 Hz, and the circuit breaker is opened. It's shown in the table and graph. And the conclusion. In this study, a smart breaker with VLC, which has the advantage of high data rate, is safe, has signal isolation and compact structure with very large bandwidth, consumes less power in the data transmission, is proposed for protection in the power system. Grid voltage and frequency information was acquired in real time with VLC using the LabVIEW software, interface developed based on FPGA. An innovative method has been developed that provides communication over light, preventing switching loss and data losses. Thanks to this structure, a technological system has been proposed that can be applied in practice, especially for the innovative protection methods required for smart grids. We want to thank Professor Dr. İlham Çolak and Ramazan Bayındır on their encouragement, and thank you for listening. And I can get your questions. Thank you.
Thank you, dear Alper. It is very good time. You completed your presentation in less than 10 minutes. Thank you for that. And is there any question from the audience? You can raise your hand or you can type in the Q&A session. In the Q&A session, I cannot see any question. I have a couple of questions for you. In this study, you mentioned the advantages of VLC, but what about the disadvantages, drawbacks, if you compare, for example, wireless communication or another type of communication? Could you please make any comment?
Well, I understood. Thank you for your question. VLC has safe because it's isolated. Isolated system because using
I mean, let me make more clear. For example, if you want to compare in terms of the price.
Okay, yes, this is very economic because it uses only LED and the optocoupler or like these devices. And it's safe and very economic and very large bandwidth and less power consumed because the information goes transmitted with light, using light, and this is very economic.
Okay, thank you. And I have comments on your results. If you just go back to I think 2 slides back. Yeah, here. I think this, I mean, the frequency change from 50 Hz to 56 Hz is not realistic because it is not common in the power system. I don't know why you increase suddenly from 50 Hz to 56 Hz. It cannot be acceptable, actually.
Yes.
And another question, for example, did you consider any international standards? Because how many periods did you consider in this study?
This study it used only I
think you didn't use any window.
I understood, but the IEEE standards only used in voltage amplitude. I can see in this study the frequency system tolerance has been chosen 10%. I show that. I thank you for your questions.
Maybe you can consider, I mean, maybe the others can consider in their future studies because
the realistic
without any standards, the presented study doesn't make sense. You need to consider the standards. Is there any other question? I cannot see any question from the audience, and thank you for your presentation. It was very, very good presentation. Thank you, Alper.
Thank you.
Have a nice day.
Thank you.
And let's try again the first presenter.
Yes, I have, sorry.
Dear Ferhat.
Hello everyone. Can you hear me now?
Yes,
okay?
Yes, I can hear you very well.
Sorry for my problems.
No problem at all.
Today, Elazığ is a bit stormy, and we had faced power outages, also connection outages. Sorry for I'm being late and for all of these problems.
No
yes,
problem.
I'm here and I'm ready for my presentation.
Okay, please share your presentation and you can start. You will have maximum 12 minutes and try to finalize your presentation within a time. Okay.
Okay, I'm getting it ready.
I can see. Yeah, you can start. Please go ahead.
Okay, is everything okay now?
Yeah, we can see your presentation and we can hear you very well.
Yeah, before starting, a bit about me. I'm Ferhat Uçar. I live in Elazığ, both working in Elazığ city, the Fırat University Electrical and Electronics Engineering Department. My background is on electrical engineering and my PhD was on machine learning, the electrical power grid signal analysis with different machine learning techniques. And after my doctorate, in my postdoctorate studies, I transferred my works to the deep learning based studies. And today we are going to talk about our study, the lightweight deep learning model for smart grid stability prediction. This is the outline of my presentation. Because the time is delicate, I'm going to be a bit fast. Thanks for understanding. First of all, everything goes to smart. Everything has intelligent side nowadays. It's very famous being a thing with smart proposition or smart adjective. And also our electrical grid needs to be smart because smart grid, first of all, is a state-of-the-art power grid framework, and it also manages renewable energy sources integration, and it also allows the electricity flow in both directions. And today everything is different from yesterday. The consumers also produce the electricity and sell them to the production companies, gives their energy to the grid, and the management of the energy is very important. And the smart grid takes the scene at this time. And first of all, I would like to draw your attention to grid stability. What is grid stability? The first thing rises in our mind is there is an equilibrium between production and consumption. We have to provide this. And because the electricity cannot be stored in transmission grid, we have nowhere to store it. And so the amount of electricity fed in must always be the same as the amount of the electricity fed out. So this means the production, and consumption of energy must always be balanced. And we understand this from the value of the frequency. And also the primary controls in our power plants is made by this frequency control. And here I'm talking about the grid stability in terms of the economical aspects, and also the demand response management. Yeah, demand response management is the keyword here. And the electrical energy tightly, the management of economic management of the electrical energy tightly depends on the option whether buying or not buying the energy at a certain price. This decision is so important for the companies. And on top of that, smart grid itself has advanced self-monitoring and self-healing systems in its framework. And there are a lot of data analytics, there are a lot of data measurements. And all those concerns and decision makings has developed an attention to the smart grid stability. And when we came to this point, the central smart grid control system takes its place. The control system takes just the frequency of the grid, and its oversupply situation increases the frequency of the grid. We also know that an oversupply situation increases the frequency value, and vice versa, an underproduction situation decreases the frequency of the grid. So this frequency value signs out this balance or unbalanced situation. But why we need our model in here? Why we need a deep learning based intelligent model here? Because this control system, and we call it from now on DSGC. This DSGC includes complex, very complex mathematical equations based on differential equations, and it has lots of parameters, independent parameters, as the power balance, the response time, and the elasticity of energy price. All of these are on the table and being computed in our control system, and there are lots of equations, lots of assumptions also. And all those are picturing complex mathematical models we can say it's a black box. We think about a black box. It has inputs and it has two outputs, as the grid is stable or unstable. And here the end game is solving these binary classifications, as I said. And our proposed model includes a lightweight convolutional neural network. Why I determine it as lightweight? Because it is built from scratch. It's very easy to build structure. And it is not pre-trained. It does not use pre-trained networks. They are very heavy computational costs. And the contributions in here is building a lightweight convolutional neural network, and we can see it from now on CNN, to design a lightweight CNN to predict the smart grid stability. And this design deep learning-based model performs well in this stability assessment. And using this comprehensive smart grid stability public datasets, it helps us to picture the performance in a good manner. We use it here a public dataset, a comprehensive public dataset. Sorry. Yeah, I take your time too much and a bit faster again. The CNN model is very simple and built from scratch, as I say. It has only one convolutional layer and fully connected layers at the end of it, and just makes the prediction as stable and unstable. And generally, CNN is known using the 3D images, you know. But here, we designed a 1D form of it, because it's a 1D signal, not image processing here. Here is our features. We call it features, but we can say it as inputs. Our inputs, here we can say a 4-node system. Because of this, they are beginning from 1 and 2, 4. Because in here, our modeled grid system uses 4 nodes, and these are our inputs, and you can see the output is stable and unstable. So our deep learning based model learns the black box. We don't know the complete complex computations in it. We shouldn't know it. And our model learns it. And this is the classic neural networks logic, as everyone knows. And our output is smart grid stability prediction. When it comes to results, the experimental analysis, by the way, the experimental analysis I will done in Python program, it's specific package PyTorch, and then it has automatic tuning in it, parameter tuning in it. The performance evaluation metrics, are here: accuracy, sensitivity, specificity, and precision, and also F1 score is our last evaluation metric. And you can see here, it reaches very well performance values. Accuracy, sensitivity, specificity, precision, and among F1 score needs to close to 1. As a conclusion, our proposed model reached an accuracy value near to 1, the maximum value of it, and with just using a lightweight 1D CNN structure. And in the extended paper, you can see that in extended abstract, we had a benchmark study. It reaches nearly our results, but with a complex classifier model. Our model is very simple and very cost effective. And the proposed model solves the DSGC's assumption issue with a deep learning-based prediction model of grid stability and reaches high performance values in renowned performance criteria, as you saw before. And soon, we are trying to enhance the study with different DL-based models with rich data analytics in it. Yes, thanks for listening.
Thank you, dear Ferhat, for the nice presentation. Is there any questions from the audience? If you have any question, please raise your hand or you can type in the Q&A session. I think there is no question from the audience. I have one question, actually.
Yeah, sure.
When you were presenting at the beginning of your presentation about the balance of the power system, okay, as you know, the balance is, we can divide into two main parts. One is the frequency balance, the second one is the voltage balance. I mean, the active power balance and the reactive power balance. In your model, did you consider both, or you just use one of these powers? I mean, the active power or reactive power, or did you consider both? Can you make comments?
I don't consider the power side actually, because the public dataset is ready to use, and they made the experiments in order to considering the voltage stability and the grid stability, the bigger picture, and generates the outputs according to their inputs about nodes. And so I'm restricted to these data sets, and I don't consider the reactive or active power.
I mean frequency stability and the voltage stability. Did you consider both, or only
both?
Okay.
Yeah.
Okay, then you use both active and reactive power stability as well. Okay.
Yeah, relatively. Yeah, relatively. Okay. Yes, I see.
Thank you, Ferhat. I think there is no more questions from the audience. Let me just check the Q&A session. No, there is
again.
No,
I apologize for my problems at the beginning. Sorry.
No. It's okay. No problem at all. Thank you. For
thanks everyone.
Now, let's move to the next presentation. The title is A Supervised Learning-Based Method Using a Modified Voting Algorithm for Classification of Complex Power Quality Disturbances in a Hydrogen Energy-Based Microgrid. And this study will be presented by Gökay Bayrak from Bursa Technical University. Dear Gökay.
I can presentation.
Yeah, but I think, I don't know.
Alper Yılmaz.
I can see the Gökay in the list. Why he is not going to present? Because you are going to present, Alper?
Yes.
Okay.
Yes, sir. I will start. If you can see my presentation.
Yes, please go ahead.
Thank you. Thank you again for your participation. The topic of my second presentation is supervised learning-based method using modified voting algorithm for classification of complex power quality disturbances in hydrogen energy-based microgrid. And my outline, as shown in this figure, outline of my presentation. First, I will talk about introduction, and then I will explain our supervised learning-based method using modified voting algorithm, weighted voting algorithm, and its theoretical backgrounds. And finally, I will give the results, and I will finish the presentation with conclusion. Sustainable power flow is required for both the consumers and grid side to provide a reliable grid integration, especially in microgrid structures, for example, SOFC systems, PV systems. Especially on the production side, there are renewable energy sources such as fuel cells, wind turbines, grid-connected photovoltaic systems. On the consumption side, there are loads such as electrical vehicles, fuel cells, nonlinear loads, and their number is rapidly increasing also. This situation brings with the important changes in the traditional grid structure. Among the renewable energy resources, fuel cells stand out with the development in recent years. The integration of hydrogen energy-based systems, for example, SOFCs, whose number is rapidly increasing and its effects of power quality have become an important issue. highlights of our method. A new modified weighted majority voting mechanism is proposed to classify complex power quality disturbances in the hydrogen energy-based systems in the literature for the first time. The different deep neural network models are used for classification, deep convolution neural networks, deep long short-term time memory, and its hybrid model. There is 3 model is investigated this study. And existing machine learning methods are compared with the deep learning and our proposed method under noisy and noise-free conditions. The classification accuracy under low level noise and high level noise condition is respectively high the other methods in the literature. In previous studies, automatic identification of power quality disturbances was divided into 3 stages. A sanal analysis using time frequency analysis method, for example, Fourier transform, Weyl transform, S transform, Gabor filters. Feature selection using optimization methods, and event classification using multi-class classifier. There is a 3 stage. But our method, a closed loop feedback, which is not in the classical 3-step process, and the desire to eliminate human involvement were the inspiration for the proposed deep learning-based method based on automatic feature selection. And power quality is directly related to voltage and current characteristics, and a problem that leads to deviation from the ideal waveform is called the power quality disturbance. The problems occurring in the hydrogen energy-based microgrids show similar features to conventional systems. However, these events in these applications are more challenging to identify than traditional power system. Well, do I mean here? As with conventional systems, short circuit faults, large power loss, and large copper banks will lead to transients, sudden current voltage rises, voltage fluctuations, harmonics in the microgrids. On the other hand, some situations cause power quality disturbances specific to microgrids, such as enabling or disabling distributed generators like solid oxide fuel cell systems, PV systems, inverter control strategies, and operating mode switching, the presence of nonlinear loads. It's clear that the microgrid structure is the most crucial part of the smart grid, and it has become imperative to create a high accuracy, power quality, disturbance detection, and classification method. And the schematic view of the solid oxide fuel system and photovoltaic system based DG system has been shown in this figure. The system consists of PV plant, SOFC system, main grid connection, breakers, linear and nonlinear loads. Several parameters for generated power quality disturbance signals is the fundamental frequency value is 50 Hz, the sampling frequency is 10 kHz, the number of cycles of fundamental frequency is 10 cycles, the number of samples for each class is 2000, the amplitude of the peak signals is per unit. And the most common power quality events are voltage cycle, interruption, harmonics, flicker, oscillator transient, impulse transient, spikes, notches, as shown in this table. And theoretical background, we say that 3 models we used. First model, deep CNN model. Several models have been formed in this work by changing various parameters such as ordering layers in the deep CNN structures, filter dimensions, activation functions, candle dimensions, optimizer functions. In deep CNN architectures, there are input, convolution, activation, pulling, fully connected, dropout, and classification layers, as shown in this figure. The deep convolution neural network model structure for the PQD classifier system has the most acceptable accuracy rate, shown in this figure. And the long short time memory models are a type of recurrent neural network. We say LSTM. LSTM models designed to overcome the vanishing gradient problem. Models using multiple LSTM layers are called multi-layer LSTM or deep LSTM. We say DLSTM this study. For PQD classification, both single-layer and multi-layer LSTM models have been examined, and the most successful accuracy deep LSTM model is shown left side figure. And the hybrid model, generally these combinations, deep CNN and DLSTM models are called the hybrid model. The features obtained from the deep CNN method used for the DLSTM model input, as shown in this figure, And the end of the model, we use full connected layer and the softmax for classification. And our method and classification method, what is the differences? Conventional automatic identification methods of power quality disturbances generally have 3 stages. I said that. And these design analysis methods have heavy computation burden. Besides, these methods are prone to be affected by the noise signal, and the optimization process of feature filtering is complicated and time consuming. And in this study, a hybrid model using a multi-class classifier, we said 3 model we used, investigated. And its flowchart is shown in figure. And we use 2 voting method, and one of the classical voting method and second one weighted majority voting method, or proposed method. Weighted majority weights were selected with an alternative method based on validation dataset accuracy results. For every classifier, we analyze the classification accuracy rate for every class, most confused classes for every classifier determined. For these classes, the weights of the classifier decreased. Also, weights are increased for the classifier. And we performed the experiments using these models. For every method, we did several experiments to find the best model. We determined the most confused classes and best predicted classes, and they shown in first table. And for focused classes, weights decreased with 0.7 AI, and for best predicted weights increased with 0.7 AI value. In here, AI value is the coefficient, increment or decrement coefficient in here. The performance scores of deep learning based methods are given in the second table. The proposed method using weighted majority algorithm accuracy is higher than the other methods. Also, with a 40 decibel noise proposed model, it has the best scores with the validation accuracy of 98.12% and the test accuracy of 98.5%, as shown in this figure. And the performance comparison of existing method, as shown in table, the Evans classification accuracy corresponding to the proposed method is higher than all the other investigated methods. Also, as shown in table, Weyl transforms, Gabor filters, S transform, Fourier transform are used in many studies, but it has many deficiencies, especially in the analysis of noisy signals. Their accuracy decreases. The noise, as the noise ratio in the signal decreases, the accuracy of the methods in the literature has decreased. This shortcoming in the literature has been eliminated with the proposed deep learning based method. In addition, 19 single and multiple power quality events were classified in the study. This is a huge amount. And the conclusion, in this study, a new hybrid multiple deep learning architecture-based classification method using modified weighted majority algorithm mechanism is proposed to classify complex power quality disturbances in hydrogen energy-based and PV-based microgrid. The proposed hybrid method's performance is investigated by comparing it to different machine learning methods. As a result, our proposed method provides reliable and easily usable results in the classification of PQDs in hydrogen energy-based systems. Also, our proposed method has significant advantages in noise immunity and accuracy. It is also suitable for big data analysis of PQD data, considering the rapid growth of monitor devices in distributed generators. Modified voting method performance is better than the classical majority voting algorithm. Publication from our smart grid labs has shown in this figure, this table. And thank you again. Thank you for listening, and thank you for your attention, and I can get your questions.
Thank you, Alper. It was a really nice presentation. I can see 2 questions. Ferhat.
Thank you. Okay.
Ferhat, you can ask your questions.
Yeah, can you hear me? Yeah.
Please go ahead.
Yes, I can.
I would like to thank you, Alper. I would like to thank Alper for this nice and interesting study. I've got 2 questions. First of all, do you use the raw PQ disturbance signals? did you convert them to image or just reshape the signal?
Just one signal. Just one signal, not image or. Like
I saw that you used 2D CNN construction. So you're supposed to be convert them.
1D. Maybe this is an error. We use 1D signal just.
In the figure, I saw 2D. And I thought you reshape.
That may be 1D. Sorry for that. This must be 1D.
Yeah, I thought you. Yeah, reshaping them. And my last question is.
Thank you for your attention. Sorry for that. Thank you for.
Is the proposed model is a bundle model? I mean, it includes 3 types of classifier. You use both of them, and
yes.
you know. Do you point out a one? Because I see in the last table a bolded result at the bottom of the table. There is one result. You give us the proposed model's result. Please, the last one, the last table.
I see.
I think another table. You make them both the one result. Yeah, this automatically one, the proposed method. What is this result? This is the, I think your algorithm runs all of 3 models and the maximum win-win model. I think I don't understand that.
Yeah, we use validation accuracy rate for each classes, and we choose the best predicted classes and most confused classes. For example, deep CNN neural network has the best accuracy. We use it, or DLSTM has best accuracy. We use it. Yani,
winner takes all. Winner takes all.
Yes.
Yes.
Yeah. Decreases and increases and the coefficients. We choose the best one, and the one classifier is applied the signal.
So when you give me when you give the last model to the end user, the algorithm, you give all of 3 models and say, run all of these 3, and our algorithm.
But the perfect one is selected for classification accuracy.
Okay, thanks, thank you.
Thank you. Thank you for your questions.
And I think there is no more question for you, Alper. Thank you for your presentation again.
Thank you.
Have a nice day. And the next presentation is nature-inspired 2-layer optimizations for interconnected heat and power multi-microgrids. Will be presented by Paolo Fracas from Italy.
Hello, I hope you can hear me and
see
me.
Can hear you.
Okay, very good. Let me enter in the full screen. Okay, thank you for giving me this.
Sorry, before starting, there is background noise. I don't know whether it's coming from you.
Can you now? It's better. Is it okay now?
Yes.
Is there some noise? Probably it's. I cannot delay this noise. It's the overall.
Okay, please go ahead.
Sorry, I tried to switch off.
Now we cannot hear you.
Can you hear me now?
Yeah. Can you please close to mic? Close to the mic.
Can you hear me now?
Yes. Yeah.
Better?
Please speak loudly.
Is it better now?
Yeah, it is much better. Yeah.
Okay. So it was just the handset. Sorry. So thank you for giving me the opportunity for my presentation that has been focused on novel optimization algorithms to designing a new concept of a multi-microgrid. My name is Paolo Fracas, and I am the CEO and the founder of GenForce. In my presentation, I hope it's not one moment. Okay. In my presentation, there is some delay anyway, I want just a short summary. My presentation, we started to introduce, giving just an introduction of my companies. Here you see my what we do. Basically, the company is dealing with hybrid fuel cells since almost 20 years. We design from portable to large stationary 100 kilowatt fuel cell systems. In this picture, there are some examples. But coming later, I will give just an explanation of the motivation of my work, if it's okay. Then what are the objectives of the optimizations? I will explain what is the approach that is utilized for the optimization of the microgrids, and a few examples of and results correlated. Final consideration will complete my speech. Global warming and increase of energy demand, as all we know, is dramatic change to be addressing with new energy technologies. Unfortunately, the actual energy mix, as you can see on the right side, is mainly fostering the centralized unidirectional power systems that is bringing, generating energy from thermoelectric power plants to and some small fraction of renewables to house factories. And this is mainly correlated to unpredictable energy production of renewables that is unable to match the demand. Luckily, the digital transformation of energy system give the ability to connect the peer-to-peer level loads and distributed generators into one small system named the microgrids. So the user can become in the future a producer of energy and contribute to improve the overall stability of the grid, reducing the cost of the energy. It becomes basically a virtual power plant. In my work, I've been interested to investigate a special case of microgrid, so-called combined heat and power microgrid. Where these two microgrids can exchange energy, and my aim is to study this type of technology, finding if there are best configuration, best fitting to find a large application in the future in many industrial and commercial applications. However, as we know, microgrids is a challenging technology. In order to find the best sizing, the best configuration, the best location, you needed to overcome and to solve many challenges and find the optimal configuration among the quality of energy, the norms, the reliability of the grid, and so on. So you need a high computing research to obtain an answer to this problem. In my work that I will explain, that's basically being focused on finding an optimal design and sizing and size of microgrids and operation simultaneously. And as a fitting estimator, I utilize the internal return rate combined with levelized cost of energy that returns a ratio between the energy, the total cost of ownership and the energy generated by the microgrid. And as a product that are exchanged among the microgrid and to the main grid are considered the electricity, the heat, but also the hydrogen can be utilized, it can be produced on site, and other byproducts like water that can be generated by the fuel cell, or carbon black that can be utilized by thermal plasma decomposition system. So the overall, let's say, configuration is shown in this picture. On the red line are interconnected different distributed energy resources like solar power, solar panels, wind turbines, fuel cells, battery energy storage systems, and in the red line, all the heating systems like electric boilers, heat pumps, thermal collectors, and so on. And they can exchange the two different thermal electric microgrid energy among them to find the best optimal energy, cost of energy. One moment. Okay. Now, to solve these complex problems, I developed a novel two layers optimization algorithm. At the upper levels, a new evolutionary algorithm supported by a machine learning algorithm is delivering a trial setting of configuration, sizing of distributed energy source of best of candidate locations. And the lower levels utilize these settings to estimate the optimal energy balance at the minor cost with a sequential least square algorithm. The objective equation for the inner layers, it's a combination of the revenue stream and the cost. So I need to minimize these functions by balancing the energy flows every time step, while the fitness function for the evolutionary algorithm is a combination of the actual levelized cost of energy and the internal return rate. The most interesting aspect of the evolutionary algorithm is a novel concept in the technique for the development of mutant and trial solutions. I've been inspired by, let's say, the COVID eras, by how the immune systems reacts against antigens. So basically, the mutant is evolving, is a strategy, but always managed by the diversity of the population of solutions. While the crossover recombine the mutant with target vectors with two different techniques. The traditional vertical gene transfer and the most, let's say, unusual but exists in the nature horizontal gene transfer that combine a piece of genes like coming from virus to an existing genetic genotypes. So the results, as you can see, it's shown in this graphic where basically the blue line shows the performance of this novel evolutionary algorithms. It converges quickly to the global minimum, while a traditional evolutionary algorithm, that differential evolution, are more are sleeping and on a local minimum, and are not able to find solutions quite relevant, which lower minimum like the artificial immune algorithm. Now, this algorithm has been utilized for explaining different scenarios that I studied, that are based on two different price policies for the energy exchange for the product selling. The so-called high policies, that is and a scenario where the energy cost a little bit high than today, and low policy that the energy can have a cost like it is today. The first scenario that I want to introduce is what the advantage of interconnecting the two microgrids. Here are the three scenarios. In addition to the interconnected microgrid, the two microgrids can exchange energy only with the main grid, but they are not interconnected. And the third scenario is only a load that is powered by the main grid. The result shows that basically the cost of energy returned by interconnected microgrid is much lower than the other scenarios, and the internal return rate is dramatically higher. The mix of distributed energy resources that are optimized here is a combination of renewables with mainly fuel cells and main grid. In a second scenario, okay, in the second scenarios, it's been shown how the price policy of hydrogen can have an impact on the overall configurations and results. Here, you can see that with the €3 per kilogram, is it possible already to obtain a very high internal return rate in south of Europe, in Catania, while in Bremen, the similar result can be obtained with €1 per kilogram. Again, a good combination is obtained by combining photovoltaic and wind turbine with a fuel cell. And the electric grid is always utilized to provide an energy demand response to the main grid. A third to analyzing which is the best siting, off-grid and on-grid for both for North Europe and South Europe. Has been found out that one of the best candidate area for multi-microgrid is in north of Denmark, while for South Europe is the east part of the Mediterranean Sea near Greece. Again, the best results are obtained in South Europe, where the efficiency of renewables are higher than North Europe. Finally, four scenarios is comparing of technical economic results using a green hydrogen, that means hydrogen coming from a large wind farm, or blue hydrogen that can be produced on site with the thermoplasma decomposition technologies. This latest technology has advantage. It is quite green and can produce also carbon black. It is a good high quality product that can be sold to the market. The result shows that although the green hydrogen always is a leading solution in terms of financial performance, blue hydrogen can be a bridge technology until green hydrogen is available for microgrid. So to conclude, my presentation, I just give shortly an introduction of multi-microgrid, heat and power microgrid. That is quite new technology, has not been explored in much details. For finding optimal solution, configuration needs a highly computing resource. I found a good compromise utilizing two layers optimization algorithms with a hybrid model combining analytical technical homogeny model with a machine learning models. In all the configuration, we can see that fuel cells with renewables can play key roles in these future technologies. However, favorable technologies for demand response should be in place. And another interesting result is that energy storage in any form, heating and electricity, has less advantage than converting energy in different form and bringing this energy among microgrids and below. We can shortly say that the advantage of this new technology is that heat electricity is a swarm, like fish. They're moving around, and this is increasing the overall efficiency in the energy management. Thank you for listening. I am ready for any question.
Thank you, Paolo. It was really very good presentations. I hope you can hear me. Maybe
yes, I can hear you. I hope I was clear. Because,
your voice was clear and your presentation also was very good. I would like to ask audience whether there is any question for the Paolo. Let me just check. cannot see any question. Okay. Now, I would like to ask you one question. As you know, the main issue of the microgrids is maybe one of the main issues of the microgrid is the control. I mean, because you need to employ the primary, secondary, and the tertiary control to ensure the stability of the microgrids. And in your study, you used multiple microgrids, and I think it is pretty complex system in terms of the control. How did you use your control in the model? I mean, what kind of control? I mean, for example, in your main block diagram of the microgrids, you have multiple renewable energy sources such as PV, wind, and this source intermittent nature. Did you consider all of this one in your model, or how did you run your model actually?
Thank you for this interesting question. First of all, I would say that I can give you a double answer. In a practical answer, we know we tested your challenge, the challenge of the controls in reality my companies when we try to combine in a small, very small, combining QS cells and simulate solar panels. And usually that's for small systems that's we are able to manage with additional controls. We don't find any specific problem for the management. But again, I'm talking about a combination, for example, of QS cells with a simulator of solar panels and to generate. And that's an easy exercise, I would say. Talking about the demonstrations, my presentation, and my presentation deals only with the technical economic model.
Okay.
That means my model does not take care of the controls, except for the balance, energy balance. So in our static models, okay, there are not any dynamics.
Okay.
So I needed to my problem is basically a non-linear convex problem, quite easy to solve with a sequential least square programming algorithm. Every time step, we always convert, and because there are not any issues of instability that you mentioned, I didn't take care in my. This is a technical economic model.
Okay. Thank you, Paolo. I think there is no more question for you, and thank you again for your nice presentation, and hope to see you physically in.
I hope. I hope to come in Istanbul. I like a lot.
maybe next year. Thank you again, and we are moving to next presentation. Adaptive control technique for grid integrated SPV generating system for power quality enrichments. Will be presented by Dinar Prasad from Delhi Technical University.
Hello.
Hi.
Yeah, I'm audible.
Okay, could you please share your presentation? Yes. Paolo, could you please stop your sharing? Yeah.
Okay.
Now, please go ahead and share your presentation.
Yes, I hope my presentation is visible to everyone.
Could you please make it in presentation mode? Yes. Okay, that's fine.
Yeah. Now.
Yeah, please go ahead.
Yes. Thank you once again for inviting me. I am Dinar Prasad. I'm a research scholar in Delhi Technical University, Delhi. Now my topic to the presentation today is I'm talking about the adaptive control technique. Basically, it is for grid integrated solar photovoltaic system for power quality enhancement. So these are my introductions, outlines. Basically, I will discuss about the introductions. What are my system layouts? I will discuss about what I am taking the parameters for the simulations purpose, basically, MATLAB simulations. Then I will discuss about my proposed technique, control technique, that is adaptive control schemes. Then I will discuss loss estimations by fuzzy logic controllers. Then I will discuss the simulation results and some discussions on it. So we know in our world, the global warming is increasing day by day. So we are basically moving towards the renewable energy sources for the supply of energy. So if we talk about renewable energy, that means we are talking about the clean source of energy. So there is a various kind of renewable energy sources are available in the nature. Out of that, we are talking about, we are considering solar photovoltaic sources, which is a very emerging sources. Because of that, they are environment friendly natures. They are available in very abundant quantity. So this solar photovoltaic system we are using in grid connected mode. As we know, that can be used in grid connected mode or islanded mode both. So we are taking about talk about here in grid connected. So we know that from the solar photovoltaic system, for maximum power extraction, we use technique, that is MPPT technique, for maximum power traction. And this is for the design of MPPT. We have been focusing various points, that is how the MPPT is designed. That is based on their accuracy, their reliability, what were their structure, what were their speed of convergences, and what are their costs. So there is many algorithm is already presented and implemented and discussed in various literatures. So out of that, if we talking about grid integration, the role of power electronics is increased. And we know day by day, the power electronics nodes is also increasing day by day in every aspect. If we talk about domestic natures or if we talk about the industrial natures. So if we integrate them, there is an issue that is known as common issue, that is known as power quality issues, which is and another one is there is an intermittent behavior of solar photovoltaic system, which makes the grid unstable. So there is a various research are going on, and there is various new techniques, new control techniques are implemented for how to minimize the power quality, how to reduce the power qualities. So one of the best technique is SAPF, that is called shunt active filter in a distributed system, that can reduce the current related power quality problem. Like already mitigated through the VAR compensator, PCR, PCSC, and power capacitors. So we know the distribution static compensator, that is known as district form, is a base providing technology is applied to all mitigating all current related problems. So basically here we use D-state form for reference current signal generator. So these are the main attribute of my proposed work and my work. I have discussed here proposed fuzzy logic based scheme for better harmonic filtering capability under variable system frequency. System shows the better performance for load balancing with variable irradiance and load unbalancing. The error in a DC link voltage is computed and a rule-based fuzzy logic controller. Generally, previously we use a general PI controller that can be eliminated by the fuzzy controller, which can increase the dynamic performance also. This proposed controller, that is adaptive controller, showing the excellent dynamic characteristic during the transition from solar photovoltaic system to a D-state form and then vice versa. So this is my system layout. This is a photovoltaic system. We are taking 100 kilowatt photovoltaic system. There is a load, that is linear and non-linear load. There will be a boost converter we used, MPPT we used, 3-leg voltage source converter, fuzzy logic based adaptive control algorithm is used. Here is the ripple filters, interfacing inductors are used for the removal of the system. We are taking this, this is the system parameters of solar photovoltaic. We are using NP, that is number of module in parallel is 66, and number of cell for the design analysis is 5, other is taken like this. And for the interfacing, like we take DC link voltage is 700 volt, boost converter inductor is 4.4, DC link capacitor as 300 microfarad, and based upon this formula is given in literatures. So I will talk about adaptive control system. This is also integrator based integrator. So remove the harmonics or eliminate the harmonics from the load side. So basically, this is adaptive control scheme which is shown in this figure. This is a basic control system which can be solved by simple block set, MATLAB block set or simple calculation. Through that, we can calculate the IFA for the current extraction from the phase. This is for the phase A. Similarly, we can extract current from the phase A, phase B, phase C. Basically, we are talking about the 3-phase system. Then we used this 1/3 of this all current. Then this W1, W2, W3, we take an in-phase component, WPC, WPB, WPA are the out-phase component. So basically, all this feed-forward component are used for the dynamic performance improvement. Fuzzy logic controller we used for the basically loss estimation of VSC. With that, we get the current, that is ISA star, ISB star, ISC star, and that we compare with this source current or this grid side current for the generating of voltage source converter. So this is we using fuzzy logic controller. We use for the loss elimination in a DC bus voltage and adjust. You can use to adjust quickly to the reference voltage. So DC bus voltage is getting from the MPPT controller. This is general fuzzy logic controller. Having codification, we use rule evaluator, rule base. Basically, this is 5x5 25 rule base are used for the evaluation rules we are using basically. So these are the simulations results under variable irradiance. You can see the irradiance will be around 700 kilowatt per meter square. Then after 0.4 second, they will increase to 1000 watt per kilowatt per meter square. We can see this grid DC bus voltage is almost constant. This is the feed forward component is increased correspondingly. Their PV power will be increased, their current will be also increased, and more importantly, we will see the grid voltage and grid current will be constant. And this grid current will be reducing after as the solar radius will be increased. This is compensating current. This is the load current nature. We can see this is the grid power, and we can see the active power, and this is the last one is the reactive power. This is almost 0. That will be means their power quality will be improved. There will be good power factor. We can see this is the behavior system under load unbalancing. We can take the load unbalancing in between the 0.4 to 0.5 seconds. You can see on that condition when the solar radiance is taken as 1000 kilowatt per meter square, this load current will be for the phase A will be disconnected, this compensating current will be changed, but most importantly we will see this DC link voltage will be almost constant to 700. But again we can see this grid current will be completely sinusoidal in nature. So this is the load current, this is the compensating current again, this is the feed-forward current, DC link voltage is almost constant, and this is the conditions when the frequency will be changes. After 0.4 second, 0.5 second, we can change the frequency, that is 2πf. After varying the frequency, again DC link voltage will be constant and the grid current will be sinusoidal and balanced in nature. So this is the again load balancing condition under variable frequency conditions. We can see again for the this is for the linear load. We will discuss linear load and non-linear load both case. On that case, we can see also the grid current will be balanced in nature and the DC link voltage will be constant. So this is the harmonic analysis. This figure A is showing for the balanced load. Figure B will show for the unbalanced load, and figure C will be the unbalancing conditions. We can see on all conditions we can we will do FFT analysis to determine the harmonic. What TSD will be present in the nature. So through that we can basically improve the power quality by the using of fuzzy controller. We improve the dynamic performance. So this is the conclusion. A three-phase grid interface solar photovoltaic system is implemented and controlled using the fuzzy logic-based adaptive control scheme. This scheme has been effectively used for the extraction of reference current and providing gating pulses for VSC. This proposed control technique for solar photovoltaic system has been found satisfactory under the linear load and non-linear load, and under the conditions of load unbalancing conditions, and under the system variable frequency. The proposed system, along with fuzzy logic-based adaptive control system, has shown the better performance in power quality enhancements. The effectiveness of feed-forward component has been presented for dynamic performance improvement. The TSD has been reduced very much using fuzzy logic controller, ensuring good operations of shunt active power filter and resulting in improved power quality. So this is from my side.
Thank you, Prashad, for the presentation. Is there any question from the audience? Prashad, when you run the simulation, did you select the gradation of the PV constant, or because I couldn't see any?
Sir, I have taken different case. One is, can you see? Actually, I am disconnected. I thought. So this is the first case. We will check the irradiance will be changes at 0.4 second. Initially, that was 700 kilowatt per meter square.
No, I'm not saying this one. You know, in the practice application, the irradiance cannot change like this. You know the PV curve. Did you run under let's say some certain PV curve, or you just apply step change?
Actually, I have done in this stage only the simulation work, sir. I haven't done on the practical aspects now. I have planning to do next to simulation means hardware work.
Okay, and another point is that in such application, the size of the passive components are very critical.
Yes, sir.
Okay. Did you optimize the passive component size? I mean the capacitor, inductance as well, or you just select
that will be selected according to this formula, according to what are the rating, what are the loops. Accordingly, we select this all component.
But did you use any optimization technique to optimize this parameters, or you just use the well-known equations to obtain the capacitance and the inductance values?
as of now, I'm just using the equations and get the results, and
thank you.
That value will be used.
Okay. Clear. Thank you, Prashant.
Thank you so much, sir.
And let's move to next presentation. Bit optimization in electricity markets will be presented by Ezgi Polat from Yıldız Technical University.
Okay.
Yeah, we can see your presentation.
Okay, thank you.
You can start, please go ahead.
Okay. Hello, everyone. My name is Ezgi. I am a PhD student at Yıldız Technical University in Department of Industrial Engineering. And also I work as a research assistant at Işık University. Today I'm going to be talking about a new bit optimization approach in electricity markets. In this research, me and Mr. Güler from Yıldız Technical University and Mr. Ulukuş from Istanbul Technical University work together in this research. Actually, I have divided my presentation into 4 main parts. I'll begin by giving general information about electricity markets and bidding process, and then news vendor problem. And I'll go on to the literature review, and then I will continue with our application. And finally, I will show you our results and mention our future works. Now let's start with general information about electricity markets. The regulation and privatization of power sector creates a competitive electricity markets all over the world. Also, the number of renewable power plants in the market is increasing rapidly. In this competitive environment, power generation companies desire to develop highly accurate forecasting tools and effective bidding strategies. And now I will talk about electricity bidding process, especially in Turkey. Turkish electricity market is basically divided into day-ahead market and balancing power market. Day-ahead electricity market consists of lots of electricity producers who compete each others, and they want to maximize their revenues by selling their generated powers. And there are also many electricity consumers who buy the generated electricity. These producers and consumers submit their bids to an independent system operator, ISO. And ISO matches the supply offer of a producer and demand offer of consumers, and determines the price of electricity for each hour and each hour on the next operating day. This is called market clearing price. And when the operating day comes, there may be imbalances between the bid and production. In the balancing power market, supply and demand are rebalanced, and the new electricity price is determined, and this is called system marginal price. These imbalances cases are generally experienced in renewable power plants because renewable energy plants are directly affected by weather changes, and this is reflected in production. Here you can see the cost that the producer faces in case of imbalance situation. When producer generates more than the submitted bit, that means overproduction, they sell the excess production at a lower price. And on the other hand, if they cannot meet their bid, and that means underproduction, they are subject to financial sanctions. So they want to make a good offer that minimize these costs, actually. There is a problem very similar to our problem in inventory management literature. This is called the news vendor problem. News vendor problem optimize the inventory of a perishable good. What are the perishable goods? Perishable goods have a limited selling season. For example, fresh produce, newspaper, or fashion goods. The news vendor problem assumes that the company purchases the goods at the beginning of the period and sells them during the period. At the end of the period, unsold goods must be discarded, incurring a holding cost. And in addition, if it runs out of the goods in the middle of the period, it incurs a shortage cost. And the company wants to choose the order quantity that minimizes the sum of the two costs. Here, you can see the classic news vendor problem formula. Actually, now I want to skip this formula because I will mention again in other slide, in another slide. You know, electricity is non-storable commodity. Actually, it's storable, but it's very expensive. So it has similar characteristic with perishable good products. Therefore, we will follow similar steps as a news vendor problem by solving our problem. And now I will brief look at the related literature than the methods we use. Actually, there are 6 main approaches, but now I will mention 3 ones of them. First approach, first category involves forecasting demand and then directly it's using as the order quantity. And second category involves firstly estimating the demand distribution and using it as the order quantity. Maybe I may mention fifth one. I'm sorry. This approach, in this approach, the researchers postulate that the optimal order quantity is related to the demand feature via a linear function. This is our reference article. This is the last approach. They develop a new approach to solve the news vendor problem with data feature based on deep learning. And they use the news vendor cost in the loss function in deep learning application. This point is very important because it is the starting point of our study. We adapted this approach in our model. Now I will mention how they adapted to this approach. In left side, you can see the loss function of the reference article. This term is a holding cost and second term is a shortage cost. And I want to talk about directly our model. U is our production, T is our bid value, and PTF and SMF are our prices, electricity prices. And this term is overproduction cost, and this term is underproduction cost. Actually, we want to minimize some of these two costs and find the optimal offer by solving this optimization problem. In second line, you can see that the loss function is written in partial. Actually, this loss function we use in ANN must be differentiable, but this function is not differentiable. So we revise the loss function by squaring each cost term, and then we have an Euclidean revised loss function. Actually, this is our final version of our loss function. In this study, we develop a model for a solar power plant operating in Turkey. Our predictor variables include temperature, humidity, pressure, wind speed, solar radiation, day of the week and time of the day, and electricity prices. And our output is production, electricity production. 80% of data is used for training, and remaining 20% of data is testing, for testing. And we have 9 inputs and 1 output, and we normalize our data in the range of 0 to 1, and we have 1 hidden layer and with 15 nodes, and we use rectified linear units as activation function. And we change our loss function. We use a customized loss function. Now finally I will mention our results. In this study, we propose an optimization method to determine electricity producer bidding strategy. We establish an ANN, artificial neural networks, with a customized loss function, which considers the effect of underproduction cost and overproduction cost. This plot shows that a comparison of production and bid values over test data. Generated electricity is represented by a blue line, and the dashed red line indicates the bidding value we optimize. This plot clearly shows that the bid value we optimize has a similar pattern with the electricity generated, electricity produced. And also we compared revenues and we obtained almost 2% more revenue with the revised loss function compared to the mean square error loss function. And finally, I would like to talk about future works. Firstly, we are going to tune our neural network because we have run the neural network several times and haven't tried different options yet. We want to try this and improve our neural networks. And secondly, our data does not include the summer months exactly. We think that we will get better results if we enlarge the data to cover the summer months. And thirdly, we can increase the input variables of the problem. We think this will increase the prediction accuracy. And I think it's the most important one, the last one. In this study, we use a revised loss function. There are many points where this loss function can be customized according to the electricity market. We have started working on this and getting better results. Yes, thank you very much for your time, for your attention. our topics was much more different than others' presentation. I hope my presentation was clear. Thank you again.
Yeah, thank you, Ezgi. It was a very clear presentation, and it was not different actually. All the presentations are related to microgrids and the smart grids. Mm-hmm. And let me just check, is there any question? Yeah, Paulo, do you have a question?
Yes,
go ahead.
Thank you for this presentation. Very clear and excellent. You provide a lot of details. I have just a technical question related to your neural network, because I'm finding a similar problem. And do you experiment saturations in neural networks? I mean, you obtain same result with different input when you validate, and if so, how you solve the problem? Thank you.
I'm sorry. Actually, in this application, we don't make a prediction because we change our loss function, and we don't prediction. For example, if we use mean square error, for example, actually we can predict our electricity production. But in this study, we use we use customized loss function, and actually we don't predict. Actually, we optimize our offer. Is this clear?
No, it's clear. Okay, I understand.
Mm-hmm.
I understand. So you're more focused on the, let's say, on the management of the network itself.
Yeah.
And,
yeah.
Okay, that's clear. Thank you.
Thank you.
One of the major problem I found with neural networks is that it takes a lot of time in learning, and the results are quite poor comparing with different, the more traditional approach, like regression models. So I found in literature similar problems, people with similar problems, and it's very, one of the key features is the training, and you require a lot of data to do that. So I want just to share some experience with your work. It's very good. Thank you very much.
Thank you.
Thank you, Paulo. And we have another question.
Yes, I'm here, Ferhat. Thanks for your nice presentation, Ezgi, and this is a very interesting study. First, I thought you had a feature forecast. I thought it's so. I assumed that you run a future prediction or future forecast of these values, but now you made it clear that you don't purpose that aim. And so I would like to ask about the evaluation metrics. And so I was asking you about performance metrics. Why didn't you choose MSE or MEA, like error-related metrics? Mean square error, mean absolute error, you know, or R square. The R square shows the relation, you know.
Mm-hmm. Yes, actually, I told about this one. Okay. Sorry. A problem in my screen.
Oh, it's okay, we can see.
Okay. Actually, if we use mean square error, actually we tried mean square error, but it is about the prediction of electricity production. But we are not interested in this. We optimize our bidding, our offer, and so actually we don't make a predict. We optimize our offer, and I don't know, is this clear? Actually, but we tried mean square error, but this is a different topic. Is this clear?
Yes, thanks. Okay.
Okay, is there a question for Ezgi? I think there is no more question. Thank you, Ezgi, and good luck for your future studies.
Thank you.
And I would like to also thank all the presenters and attendees to join this session since it was the last presentation. And I hope to see you next TÜBA conferences. And take care of yourself and stay safe. Have a nice day.
Thank you.
Bye-bye.